Lecture 3, Stanford CS193p, that's right, spring of 2025. I'm going to do a little bit of demo at the start. I just want to go and finish up looking at that match marker function that we did. I kind of jumped over it quickly in the last one because we needed to get done what we got done last time so you could do your assignment 1. But then I'm going to jump back into slides, and unfortunately it's going to be the slides the rest of the day, okay? No demo today after that initial part. And this is all setting us up for Wednesday when we're going to make our CodeBreaker app do code breaking, okay? It's going to do the actual logic, and all the storage of all the pegs and all that stuff is going to happen there. But for me to do that, I really need to talk about these topics up here, model and UI and Swift type system. We need to really understand the fundamentals of those. And you are reading about those things a little bit, not so much model and UI, but the Swift type system in your reading. But I'm just going to call out some of the just key parts of the type system in Swift. All right. But before that, I'm going to, this review right here, we already did a review at the beginning of Lecture 2, so I'm not going to go and review it all again. However, I did create slides to review all of the things, and the slides are actually on Canvas, so you can go look at them there. And I know some people like to have written notes of what we did, kind of a written summary of what we did, and so I've done that for you, and we'll blast through those here just so you can see what's in there. All right, but first let's finish up this match markers thing. Here's where we left off last time. Hopefully you guys have been working on your homework, so you've done a lot of work in here since then. But we're going to focus just on this area in blue today, nothing else. And I'm going to start by quickly reviewing this whole thing about return circle right here, because I had to rush that a little bit. And someone did ask a question afterwards that I thought was a good question. So why do we have the word return right there? Well, because this match marker function returns some view, and so we have to return something, so we're returning the circles. But I said there was another way to do it, which is to actually put @ViewBuilder here. Now, why does it work to put @ViewBuilder here? See, no errors and no return. Well, that's just simply because @ViewBuilder, what is it? It's a list of views that can have lets and ifs in there. That is what an @ViewBuilder is. And if you look at match marker, it's a list of views with just lets in there. It only has one view in its list, that circle that's been modified with fills and strokes and all that stuff. But it clearly is a valid view builder, so this would work fine. One other way we could do this without that return keyword is to get rid of ViewBuilder and also get rid of these lets. If I get rid of these lets, I'll have other errors there, of course, but it's no longer complaining that I'm not returning something. And why is that? That's because in any Swift function that returns something, if you have a one-liner code, your code is only one line, and it actually is that type of thing, some view in this case, then you don't need return. It's purely syntactic sugar to make things look a little nicer, that's all. So those are kind of the three ways. I was asked, which of those three ways is best? What is best practice? And it kind of depends. And in this class, I'm going to try and show you different ways to do things. There's art of programming, right? What looks good, what doesn't. I will try and not bias you too much with my own preferred things, like array versus square brackets. But in this case, a lot of people don't like putting @ViewBuilder in front of a func or a var like that. They would prefer that you make this a helicopter view. That's what they would say. If you want to put @ViewBuilder there, then you should have a match marker, singular, helicopter view. And it takes peg as the argument and it draws it. And I can see that's reasonable. The nice thing about doing this here is that if you have other context in your view, you can just access it directly. You don't have to pass it on as an argument to a helicopter view. So it's a balance. But I can see it both ways. I personally am not as opposed to @ViewBuilder on funcs and vars because, hey, what are we doing? We're building views here. So saying @ViewBuilder, I don't quite have as much of a problem as other people might have. And this return circle is fine. This is pure Swift, right? This is no syntactic sugar or anything. But I probably, personally, would maybe prefer doing @ViewBuilder there. Let's now look at another thing I did real quick that I didn't even talk about, which is right here. I used a ternary operator here. This question mark colon, do you see a question mark colon in there? It's like a compressed little if statement. If the thing on the left exact count greater than peg is true, question mark, I'll do the first thing. Otherwise, I'm going to do the other thing. So this is like if, then, else, just jammed into a little space. Ternary operators like this, very important in SwiftUI development. And that's because a lot of what's happening in our UI, especially when it gets animated, is what's happening to the view modifiers. The view modifiers are modifying it in different ways depending on what's happening. Opacity, things are fading in and out and all that stuff. And so we use ternary operators quite often as arguments to view modifiers to control the behavior of what's happening exactly as we're doing here. And so I have two ternary operators here, that one and this one right here. Everybody comfortable with ternary operator? Any question about that? And then the last thing is this line of code, which is really where I want to focus my time today. And luckily, these two lines of code are similar. And what I want to go through here is I want to show you what type inference does to these lines of code. And I also want to emphasize how we do the inline closure that's going on here. So let's review what this does. This is a line of code that's trying to find out how many times in this matches array up here, how many times .exact appears. Right? That's what we're trying to count. So what we're doing, and it's going to return, obviously, an int. That's why its type is :int. And we're going to ask the array a question by sending it a function. This .count is just a function call on array. Remember, that's how we call functions in Swift, dot and the name of the function. And then this are the arguments to that function, count. And what count wants is a function that tells us whether to count that thing. So it's going to call this function for every single thing in the array, and you're going to return a bool, true or false, whether to count it. So do we see why this is going to do exactly what we want? It's going to count how many times match equals .exact right there. Now, that argument is of type function, a function that takes a match and returns a bool. And its little keyword is where. This where is just its keyword, just like we had image, system name, whatever. System name was just the name of that argument. That's all that's going on here. It's just where. Now, we would never write this like this. Here's how we would write this. First of all, we would not say :int. We would not say :int there because it's clear that we are counting something. It returns an int. We use type inference whenever it's obvious what we're doing. The only time we would actually put a :int there is if this function matches.count returns somewhat of an odd type that might be unexpected by the readers of our code, and so we're going to put that type there to make it clear. But taking that :int off, if I do option click, it's still an int. It's being inferred to be an int instead of explicitly, so we would not put an int there. The second thing is this closure that's in here. I'm going to show you how we get to here from this just being a regular non-inlined closure. I'm going to do the same thing I do with VStack. Remember this? When I said I'm going to make a func, I'm going to call this one isExact. And it's going to take a match as an argument, something of type match, and it's going to return a bool. And I told you that that's what the count function in array takes. A function that takes one of the things in the array, which is a match, and returns a bool. So here I could return match, that's the argument to this function, equals match.exact. That would be the full way to say this. Now that I have this wonderful function, I could go back up here and I could say where is exact. Because the argument to count, that where argument, is a function that takes a match and returns a bool. And that's what isExact is, so I can just put it there. Everybody cool with that? So how do we get from this situation, which I think we're all comfortable with, to what we want up there with that closure? Well, the first thing is I'm going to remove this return for the same reason I just talked about. This is a single line function, returns a bool. That's a Boolean expression. I don't need the return. Secondly, I'm going to remove match. Match.exact is the full name of this case right here in my match struct, match.exact. But we never would put the match here, or unlikely to put the match here, because we can clearly infer that. We know that the things we're comparing it to equals is a match. So obviously if we say .exact, we mean match.exact. So I'm using type inference to get started there. The next thing I'm going to do is I'm going to put this function in line. So I'm going to replace the isExact up there by putting this thing back in there. The way I'm going to start is selecting it inside the curly braces, and cut. And then I'm going to go up here to isExact and paste to put it in there. And let's make some space around it so we can see clearly where we are. But I'm not quite done. This is what I did for VStack, when I had the VStack that had greetings, remember all that business? But there was a little difference there. That function had no arguments, but this function does have an argument. It has that match argument right there. So when we inline a function like that, we don't just copy and paste the curly braces. We take this part, which is the types of the arguments and the returns. We cut that, and we put that inside these curly braces. It was outside when it was the function isExact, but now it's inside, and we separate it from the code by saying in. So in, the keyword in, it's just a separator between the type information about this closure and the actual code. The match equals exact right there. So that's all in is. In is just a separator. It's called in because it's kind of like these arguments in this code. Right? That's why we use the word in there as opposed to some braces or brackets or colons or something like that. In is just a nice word to separator, but that's all it does. We can get rid of this, by the way. Of course, we don't need the name isExact anymore. One of the great things about inlining a function is you don't have to think of a name of it. We're not done. We've got a ways to go. One thing is we're going to use type inference to get rid of most of this. Because what's happening here, we're passing a function to the count function of array. We already know that it takes a match and returns a bool, so we don't need all this type information here. Let's get rid of this returns a bool. We already know this returns a bool. And let's get rid of the fact that this is a match. We already know it has to be a match. It's an array of matches, so if we're counting them, of course, it's an array of matches. And Swift is also nice where we don't need these parentheses. They're not really collecting or gathering anything, so we can leave that off. Look at this, match in. Now, does this look familiar? This is exactly like we had over here in content view for each. Look at for each's little function argument there, index in. Same thing, the index is just the argument that's being passed to this little closure. This closure is a closure that takes an int in this case because we're for eaching over a range of ints, and it returns some view. So that's what that little inline closure is, and so that's why it's saying index in. The index is just the variable that's being passed through. That's exactly the same thing that's going on here with match. And a lot of times now we've made it so small, we'll just put this all in one line. Now we're getting really close. We look almost the same as this found count right here. But I'm going to take this one step further, actually 2 steps further. I'm going to get rid of this match as a named argument. I don't want to have to give it a name. I'm going to call it $0. So if you have an inline closure, you can essentially use $0, $1, $2 for its arguments in order. So $0 is the first argument to this thing, which was match. And if I use $0, then I don't have to say match in match equals that because I'm not defining match anymore. So I don't even need the part before the in. Now we're almost done. One more thing. Trailing closure syntax, right? This is the last argument to count. It's the only argument to it. Since it's the last one, I can get rid of that little where, put this outside the parentheses here. In this case, get rid of the parentheses because we don't have any other arguments after the count. So this is what we would actually write. And you can see this is much more concise. Reads nicely too. Let the exact count equal the matches array's count of things that equal exact, which is exactly what we want. Found would be the same thing here. I would let found count, no colon int, equal matches.count, where $0 does not equal no match. And you can see that the AI is clearly ahead of me and knows what I'm doing. And this is what this would look like. So this is your first exposure, really your second exposure, I guess, to seeing functional programming, where we're programming by passing functions to other functions. And this is just the start. We're going to do this dozens of times in this course. So this is something you want to get familiar with. In the future, I'm not going to break it out to isExact and greetings and all that and put it back in. I'm just going to start writing $0 equals or create something, some arguments in and start writing code. And so, I mean, I'll take it easy on you and slowly bring you towards this, but that's where we're headed. So get used to this. Any question about this? Does it all make sense? All right, this next item here is the review. So I'm going to just briefly show, I'm not going to go through these slides, but I'm going to show you what slides I've provided here. These are all the things that I believe that we've done up through what I just showed you. Right? And so for each of them, I've come up with a page, like here's our content view that behaves like a view, and here's var body and what it's all about, and here's view builder, our bag of Lego view, here's the Lego analogy itself, VStack we know about, HStack and ZStack also, trailing closure syntax, I just showed you that, closure syntax in general, I just showed you that as well, type inference, we talked about that, and there's a little bit more here about the fact that it can infer even things like var num equals 3.0, that num must be a double, it must be a floating point number versus an int. And view modifiers, of course, we talked a ton about that. Static vars like color.green, those are global variables that are namespaced to a certain type. We talked about decomposition, making our own var pegs or our func pegs, or making more helicopter views as ways to decompose our big complicated var bodies into smaller things. We got for each, one of our absolute favorite bag of Lego views that makes a view for each of something in a collection. Shapes, we talked about circle and rectangle and the fact that they have fill and stroke border. And enum, of course, which is another type, like structs are types, enums are types. And we learned about those, and therefore discrete values like match, no match, exact, and inexact. And we learned about preview, right, so that we can put some view on the right-hand side as we're working on our view that shows off what we're doing, so in real time, instantaneously, we can see what's going on. All right, everybody okay with that? That's just kind of there for you to read offline and remind yourself if you have questions or whatever. All right, so here's our two big topics today, model and UI and the Swift type system. So let's talk about model and UI. So data in our app is generally going to flow from something called our model, which is going to be like our CodeBreaker app and all its logic, through our UI into the end user's senses, mostly visually, but maybe also audio, sounds, and things like that. And when that happens, as the data flows through the UI, we want to be really clear about where the source of truth is for the data that's appearing in front of the user's face. We never want to duplicate our sources of truth and have one view think it's got the source of some truth and another view think it's got it, and now they're conflicting and getting out of sync. So let's talk about this model and UI idea. So SwiftUI is very serious about this separation between the model and the UI. And when we use the term model, this is not just a light term we use, it's a very important term. Okay, we're talking about what our app really is at its heart. So our CodeBreaker, all the code that does anything with making attempts or checking to see if match markers are matching or whatever, that's all being done in our model. Okay? And we call this model. And this model could be a struct. It could be a whole bunch of structs. It could be a SQL database. It could be some network database out there, some query, some REST API that you're pulling things from or whatever. It could be some machine learning thing that's doing something. It could be AI out there that you're asking it questions or whatever, or any combination of all those things, but it's generally not user interface. No, and this model is generally UI independent. It doesn't really care what kind of UI you build to view it. It's going to be representing the data and the logic behind it all. So you can kind of think of the UI as a parameterizable shell around the model that the model feeds with data, and so that the UI becomes a visual manifestation of the model. Okay? And you might have noticed that when we're doing our programming here, SwiftUI programming, we're not actually doing code that does something. We're doing code that declares something. Right? We don't have a for loop that goes through a for loop and calls functions and does things. We have a for each view, right, that is creating a bag of Lego of views, and then we're just putting that on screen in an HStack. There's a lot of just creating things, maybe modifying them a little, and then putting them on screen. And the model has all the data and stuff that's going to drive that. It's going to drive those ternary operators on the view modifiers. It's going to drive if-thens inside of a bag of Lego to decide which views are on screen. It's going to drive putting up new views on screen to show things. It's all going to be driven from the model. And the model, incredibly, doesn't have to do anything to make this happen. All the model has to do really is exist. And Swift is really good at noticing that something changed in the model and then understanding what part of the UI needs to change because of that change and only changing that. So it's very efficient about that. And that is all of how SwiftUI works. That's why we say that it's a declarative, reactive user interface design model. Declarative because we're just declaring what the views and the modifiers are, and reactive because it's reacting to the changes in the model all the time, automatically. Okay? That's what SwiftUI is all about. All right, so this model, which is our game pegs and matching logic, the first thing we're going to do on Wednesday is sit down and write our model, okay, author our model. And so then you'll understand clearly what a model is, because that's the first thing we're going to do. And I already said that. All right, so I said that sources of truth are really important to understand and to keep clear about where your data is coming from. And so luckily, Swift, just by its very design, SwiftUI makes this pretty simple. One of the number one ways it does this is it uses structs, okay, as opposed to classes. This is why SwiftUI is not object-oriented generally, for the most part. Why is using structs help us with sources of truth? Well, structs are generally immutable, and when you pass them around, you copy them. So if you're copying read-only immutable things, you can't have very easily two different guys thinking they have the truth, because if you can't edit something, it's not the truth of anything, it's just a copy of it, right, an image of it. So Swift naturally does that for you, and that's part of why we do structs. Now we do use classes, and I'm going to talk about in this later in this slideshow here when we use classes and why we use classes, because they don't have this nice feature. Now the other thing that SwiftUI does is it makes you mark explicitly with this thing called @state in yellow right there, when something is a source of truth. So you say @state and then some var, and now you know, oh, that is the source of truth of this var. Whatever's in this var, this is its source of truth. You have to mark it. And that's really valuable to making sure you don't duplicate your source of truth and all that stuff, because you're going to have to put @state in there. And we're going to see how we use @state on Wednesday, because of course we want to have some state. Our model is going to be some state in our CodeBreaker app. You notice I also mentioned @observable here. You notice I don't make it yellow. I just make it white. And that's because that's something we're going to talk about in a few weeks. I'm just downplaying it a little bit now, but sources of truth are also marked with this thing called @observable. We'll talk about later. SwiftUI also marks sharing of truth, because sometimes two views might want to share a truth. Both of them want to edit it, but we want to be very clear about the fact they're both sharing it. And so it has another thing, @binding, also in white, so we're not really talking about this right now. A few weeks we'll talk about it, to explicitly share some var between two views. And that's all I'm going to say about this truth and marking truth and truth sharing for now. As the quarter goes by, we're going to learn more and more about how this works, the separation of model and UI. Now, in the past, I've talked about mechanisms for separating the model and the UI, like MVVM, model, view, view model. I'm not going to talk about that this quarter, mostly because I want to just focus on the importance of the separation and of identifying sources of truth. And I want to spend more of our time working on how we use this separation to our advantage and build things. So we'll see how that works out. I probably will talk about these things a little later in the quarter, but mostly we're just going to be really clear and try to be really clear about separating those two things. All right. So the rest of this lecture is going to be about the Swift type system. So a type system in any language is the building blocks for making types, structs, classes, enums here. And the optional and extension, those really aren't type building things themselves, but they're just very important uses of the type system. So struct. Now, we're pretty familiar with struct. We already know that struct can have stored vars, and we don't see it a lot in views. When we do have stored vars in views, we have to mark them with @state. But you can imagine in our model, our CodeBreaker game, we're going to have a var somewhere which is the master code for our game, for example. That would just be a var in a struct somewhere. We also can have computed vars. Of course, var body is a computed var. We have all kinds of computed vars in structs. We can have constant lets, like let width equals 3, and then I could say stroke with line with width. And then we have functions in structs, like here's one multiply that multiplies an operand by another thing there. Now, this code right here is a little awkward. It's a little awkward both for the caller and for the person writing this particular function. So why is it awkward for the person writing the function? Well, look inside the implementation of multiply. They have a variable in there called by. That's kind of weird. It seems like that other variable wants to be called like other operand or operand 2 or something like that. By is just kind of an odd thing, but it makes sense for the caller. Multiply operand 5 by 6. That's exactly what we say, right? Multiply 5 by 6. So it makes sense. And then on the caller side, it's a little weird because it says multiply operand colon 5. Do we really need the word operand colon right there? Really what I want to say is multiply 5 by 6. So the great thing about Swift is that it allows you to have different names for your parameters depending on whether you're the caller or the person writing the code. So here's that same function, but I'm using different values for each. And essentially each operand can have 2 different names. It has the external name, that's what callers use, and the internal name, that's what I use inside my multiply. Here, the blue ones are the external names, and the purple ones are the internal names. And by the way, if you only have one, all we've ever done, then the external name and the internal name are the same. Here, let's look at the by other operand first. You can see that as a caller, I can still say multiply 5 by 6, because by is the external one. But other operand is on the inside, so inside multiply, I say return operand times other operand. And then look at the other one. Blue underbar line there, an operand. What does underbar mean? In Swift everywhere, underbar means nothing, nothing here. So blue underbar there means no keyword for this argument. And that's why I can say multiply 5 by 6. I don't have to put any keyword there because I have underbar as the thing. And then I still have operand as the name to use inside of multiply. So everyone understand what's going on here with the names of parameters to functions? We could have 2 names for every single one if we want. Initializers, I mentioned this, and I'm only actually going to mention it now. I'm going to talk about it in detail in a few minutes here. But initializers are just special static functions. They're functions on the type that are used to get a struct initialized, depending on its arguments. And you know that we can have multiple inits. Like here's struct rounded rectangle. It's got an init with corner radius that's a float, the radius. And then it's got an init which is corner size, width and height. Size is a width and height. So it might well be that corner radius just calls the other init with a width and height that are the same, that radius. I don't know how they implement it, but something like that. And we also might have inits in our model. So we're going to have some struct CodeBreaker, which is the representation of our game. And it's probably going to have some initializer that gives it the peg choices to use, you know, green and red and blue and yellow, whatever peg colors we're allowing in this game. Maybe that's an argument to it. And inside, we just have to initialize all our variables, our master code and things like that all have to be initialized using those peg choices. Of course, we haven't done an init because if you don't have an init, then you get like a default init, which is all the variables. Lets you initialize all the variables because remember, all the variables in struct have to have a value. So we need an initializer by default that lets us initialize all the ones that don't have defaults anyway. So that's struct. Now I'm going to talk about class. And I'm talking about class not because we're going to use this anytime soon. We'll use it in 3 weeks or whatever. But I'm going to talk about it because it's probably what you're used to. Okay, how many people in here have done object-oriented programming with classes? Almost everybody. So this is probably what you're used to, programming with classes. So what is the difference between a struct and a class? Well, there is a huge difference between the two, and this is what it is. A struct and an enum are value types, and a class is a reference type. So what do I mean by this? Well, value type stores its value directly in the var or let. So if I have a var x of some type and it's a value type, the value is actually stored right there in x. That's why we call it a value type, because the value of the thing is directly in the var or let. A reference type stores a pointer to that thing in that var. So that var or let just has a pointer in there, and the actual data for the class is off in the heap somewhere. In other languages, they have garbage collection or stuff to keep track of it. We don't have garbage collection in Swift. We have something called automatic reference counting, which is a little more predictable than garbage collection. But the point is it's stored somewhere else. It's not actually stored in the var or let. So what does it mean to our daily lives that structs are this way? Well, we already talked about this. The mutability of structs, whether they can be edited or changed, is explicit. Because if you put a struct in a var, you can change it. If I have an array of something and I put it in a var, I can add something to the array. I can delete something from the array. If I put that array in a let, I can't even call the function append. In fact, if you say let x equals some array, and you try to say x.append, the escape completion thing won't even escape complete. Append is not even a function on a let struct because it's a mutable function. It changes the array, so you can't do it. So this mutability being explicit is great for exactly what I was saying before, where we want to have predictable code where we know where the source of truth is. When we put it in a var, we know it might be a source of truth because now it's editable. And we take it further by saying you can't even have a var in a view unless you mark it with @state. So that's how far we take this. But mutability, really, really important here. Unfortunately, with a class, whether you put that class in a let or a var, it's fully mutable, okay? Because you're mutating it off in the heap somewhere. Now, if I have a var pointer, it means I can change the pointer, and a let pointer, I can't change the pointer, but it has nothing to do with what it points to. I can change what it points to all I want. And that sounds good, and that's what you're used to, but the problem with that is every time you call a function and you pass a reference type to it, that function might damage that thing because it can access it, it can change it. Whereas with a struct, if you pass a struct to a function, it gets a read-only copy, so it can do no damage to the copy you have. The last thing I want to emphasize is that you're not used to this. I know you're used to more passing things around, and you can pass them by reference, and you can just change anything you want, but you'll get used to it. Okay, so the question is there efficiency loss here? Because think about it, if things are mutable and you're passing them around, you're passing copies of them, read-only copies. So I'm passing copies everywhere. I'm copying arrays. This array might have 10,000 things in it, and I just passed it to a function. Did I just copy 10,000? And what if they're big things? The great thing about Swift is it only actually makes a copy on write. So if you pass someone a huge array, no actual copies made until you put it in a var. Now it's editable, and as soon as you touch it, now it's going to copy it. So it's super efficient. Right? It's doing the minimal amount of copying necessary. And if you truly had a situation where you were passing thing around all the time, it was constantly being modified by a lot of people, you could use a class. I mean, we do have classes in Swift, but generally not an issue. Performance not an issue. All right, so classes are always referred to by reference. It's always mutable, even if it's stored in a let. I just want to show you this in action. So I'm going to do a let here. CS193p is the name of my variable. It's a class. So CS193p class is a class. And classes are defined just like structs, but you say class content view instead of struct. And classes can behave like things, although we never have classes behave like a view. Views are kind of restricted to being structs. But they can behave like other things, like maybe they behave like a hashable thing or an equatable thing or whatever. They can have other behaviors. They're allowed to it. And, of course, classes can have superclasses, although we never do that in SwiftUI. We are going to use class, but we're never going to use superclasses. We're not really doing object-oriented programming. When we use a class in SwiftUI, it's just to get its reference semantics. We're not doing it to do object-oriented programming. So anyway, if I do that and I say cs193p.students equals 60, then I'm setting the var called students inside that class to 60. And notice I did that even though it's in a let, because classes are always mutable. The fact that I put that in a let, no effect. I can change anything I want. And then what if I say var or let cs193q equals cs193p, and then I say cs193q students are 300. If I do this, then cs193p's students are also 300, because CS193p and CS193q are the same thing. They're a pointer to the same thing in the heap. That's the way reference works. And this is the way code you're used to writing would work. But let's see the same thing with structs. Structs are always copied, and if it's a let, it's immutable. So here if I have let house equal big structure, let's say that's a struct, then I say house.floors equals 2 will actually not even compile if I put it in a let. See, I let house equal that, house.floors equals 2, because let is not mutable. Now, if I said var office equals big structure, then I can say office.floors equals 4 because it's in a var, it's editable. And if I say var skyscraper equals office, and then I say skyscraper.floors equals 50, office.floors is still 4. Because that line of code, var skyscraper equals office, copied office. It made a complete and utter copy of it, again, efficiently, but a copy of it. So skyscraper is now a new thing with that big structure being in that skyscraper. Its value is now in the new var. So now I have two vars there, skyscraper and office, and they're completely different. Office is only 4 floors, skyscraper 50 floors. And I'll emphasize this on Wednesday when we write our code. I'll come up with a chance where we're going to do exactly the same thing, and you'll see this in action. Now, parameters to functions are lets. So when you pass something into a function that's a struct, this function gets a copy of it, like I said, which is much safer. When you pass a class in there, the pointer gets copied, but the thing it points to, the function still has full access to it. So that's kind of danger, Will Robinson, but you can do it with classes. So let's talk about views. I told you views are structs, not classes, and they are completely read-only. You can imagine that the entire view system at the very top is in a let. So all views are completely immutable. Cannot change them. And you might ask, how is that possible? Because my UI is changing all the time. As my model changes or whatever, my game is being played. Well, what's changing is SwiftUI's underlying system is calling var body all the time and getting a different view back. It's read-only that it gets it back, but it's a new one. So this is what happens in the whole SwiftUI system. You've got this whole sequence of views, and anytime something changes that would cause a var body to be different, the system calls var body, gets the new one, and plops it in place there. You can think of it as kind of temporarily making it mutable, putting the new one in there, and then going back to being in a let, assigning it to a let. That's why we have to do this special notation of @state if we want mutable state inside a view. Because what @state really does is it actually creates a little struct called a state struct, and inside there is a class pointer to something in the heap, because that's the only way that we could have these views that are constantly having their bodies rebuilt to have state that persists. So we'll see that all in action on Wednesday. And similarly with this outside binding, actually what outside binding does is it creates a little struct called a binding that has computed properties for setting and getting the value that it's bound to. So you have these two views. The one that's got the outside binding in it is accessing it through this binding struct that has computed properties to go back to the @state in the other view. Classes, I'm making them sound bad because they're dangerous. They're these reference types. Anybody can change things. Well, so what are classes good for? Surely they have a good thing. Well, yes, they have one really great thing, which is sharing. Classes are great at sharing things, understandably, because you pass around pointers to the thing. Everybody's sharing it, read-write at all times. Now, that big advantage is its biggest weakness because it's what makes it dangerous. You're passing a class to a function. That function might damage it if it's got a bug in there or whatever. That never happens when you pass a struct to it. But sometimes the need to have sharing overpowers our need for predictability and protection of read-only structs being passed. And you'll see when we get to that point with CodeBreaker, we're eventually going to say, we have so much sharing here, we're going to make this thing be a class. It will eventually get to that point. Classes also have another big advantage. They have a very strong sense of their identity because they have a pointer. And that pointer is the same for everybody who has that pointer to that thing. It's the same pointer, so that is an identity for that thing that lives in the heap. Like in for each, remember in for each we had to do ID self, and we had to kind of tell the for each thing how to identify each of the things in the collection so we could match them up with the views. Well, when we do a for each, which is a collection of classes, boy, it's really easy to provide identity there. right? Because class is a very strong identity. Structs have no sense of identity, zero at all. And so it's very common, you'll see this happening a lot, where we define the identity of a struct by adding a var called ID to it. And there's even a whole protocol, a behaves-like thing called identifiable, which we implement, and that identifiable behavior has this var ID requirement in there. And by having ID, then structs can be identifiable. And if we have structs that are identifiable with ID, then we don't need to do that ID colon self thing that we do in for each. And in fact, there's a version of the ID self. The default for that argument is ID backslash ID. So if you have that ID for a struct, then you can just leave that ID backslash ID off, because that's the default for it. All right, so that's it, structs and structs versus classes. Let's go back to init, this special static that we use to create something, and rounded rectangle is my canonical example here. We see with this corner radius. Notice I showed you their struct rounded rectangle behaves like a view and also behaves like a shape. We know that you can send fill and stroke to it. That's because it behaves like a shape. But I want to talk a little about the inits here, some notes. One, you don't have to put static in front of init. It is a static function because it's on the type. Obviously, you're creating an instance of that type, so you never put static in front of it. You also don't ever put return. Well, I'm going to talk about in a few slides one case where you put return, but generally you don't return anything from init. You just initialize all your vars. That's all init does. It just goes through all the vars in this struct and initializes them all to the right values. Multiple inits are allowed. We already know that. Corner radius, corner size. If you don't give a struct an init, you get this default init that lets you init all the variables in the order they appear in your struct, by the way. We're going to talk more about enum because the most important piece of data in all of Swift is probably an enum, believe it or not. So an enum, we know what it looks like. Here I've got a new kind of enum. We know about match, but here's fast food menu item. It's got hamburger, fries, a drink. I know dinner is coming up, and this is probably making it worse. But anyway, this is what we're going to use as our example up here. We know that it's a value type. So if we said var x equals some other enum, we would be copying it. So now we'd have two different copies of it. We refer to each case as the name of the type dot the thing, like match.exact or fast food menu item dot fries. But we rely on type inference a lot. So we often don't type this fast food menu item part. We just say dot fries if we can. But an enum has a lot of really powerful features, and the most important powerful feature is associated data. So what does this mean, associated data in an enum? Well, each case in an enum is allowed to have any data that it wants to be associated with that case. So this is data that's only going to exist when that case is the discrete choice of the enum. For example, fast food menu item. The hamburger might have the number of patties. This is a double burger or a single burger. Fries, maybe it's large fries or small fries. And then drink, it has two pieces of associated data. One of them is a string like Coke or root beer, and the other one is the number of ounces, a 32-ounce drink or 16-ounce or whatever. Now, drink is kind of an interesting case because notice the string there, it doesn't have a name. There's no parameter name for that one like there is size and patties and ounces, and that's perfectly allowed. I probably wouldn't do that here because it's not 100% clear to me what that string would be. If it's a drink, I guess I could figure out it's a Coke, but it probably wouldn't hurt me to put brand colon and string, but I just put it here so that you can see that it's not required. You don't absolutely have to have a name for each of the things, so it's allowed not to. So things like the size of the fries only is stored in this enum if the case is fries. So it's a really great way to separate the data out. Now, when you create a enum that has associated data, you do it by saying fast food menu item dot hamburger, and then in parentheses, that keyword, patties, and 2. And for the drink case, you would just say parentheses, quote, Coke, comma, ounces, colon, 16, or whatever. And obviously, if you have no associated data, you don't have to do open parentheses, close parentheses. You just leave it off. Like cookie, it has no associated data. And one thing to note about this in terms of type inference is it can infer one side or the other, but not both sides. If I say menu item equals fast food menu item to the hamburger, of course it knows the menu item is of that type. Or if I say other item is of type fast food menu item equals a dot cookie, Totally cool, but I can't say yet another item equals .cookie. I think you were asking this. Will Swift just look around and see if there's cookie somewhere and say, oh, there's only one of them, so I'll use fast food menu? No, it doesn't do that. Strict type checking, so it's got to be sure that that's what's going on here. And of course, if you had an array of fast food menu items and that was typed, of course, it could infer from that, etc. Let's talk about checking an enum state, because the only thing we've done to check a state is use if. We said if the match equals exact. But another way to do it is to switch on it. Switch is a keyword in the language that says, I'm going to look at this thing and look at every case one by one. And a switch has to look at every case. And you just say switch and the name of the variable that you're switching on, then you say case, the name of the case inside of the enum, and then a colon, and then doing whatever code you want to do. So in this case, I'm just printing out the name of it. And notice I'm not doing anything with associated data here. There's no associated data. This would work even if we'd had that associated data, but I'm not actually looking at the associated data here. And of course, we use type inference, so we wouldn't type fast food menu item dot by every single time, right? Menu item presumably is of type fast food menu item, so we would never have that in there. So this is what a typical switch statement would look like. There is a really nice thing that you can put as the thing to do in a case, which is break. Break means do nothing. I don't want to do anything here, just break out of here, essentially. So in this case, if I have fast food menu item is a hamburger with 2 patties, and I did this switch statement, it would print nothing, because a hamburger there doesn't have a print. I broke out of there. But the other ones would still all print if it was of that type. There's also default. I told you that in a switch, you have to switch on every possible case. Well, default lets you say, and the rest of the cases are this. So here I have hamburger, I'm breaking still. Fries, I'm printing fries. And then for default, I'm just printing other. So that would work for the cookie. That's going to work for the drink. It's just going to print other. So that's default. Now, what's interesting is you can switch on other things besides enum. You can switch on a string. But if you switch on a string, you absolutely must have default, because there's no way you can have case every single string in the world. That's infinite. So you have to have a default clause if you're switching on a string. Now, I've done one-liners, right? Case hamburger, print burger. But you can actually have multiple lines. Case fries, print yummy, print fries. And one thing that's different from switches in a lot of other languages is this does not fall through. So if I have the menu item is fries, like there, you see in yellow it's fries, it's going to print yummy fries, not drink. It's not going to fall through and print drink right there. There is a keyword fall through that I could put after print fries that would make it fall through, but I don't recommend ever doing that. I think it's only in there because people come from other languages that it falls through and they think they want that. But there are other ways to share code between the cases using functions or other things that I think are better. So I tend to stay away from fall through. So how do we get to the associated data? We get through that with switch. Switch is the only way, really, to get at the associated data. I shouldn't say it's the only way, but it's the way that we get associated data. And all we got to do is same exact switch I had before, but I'm putting parentheses, let, and some variable name for each of the pieces of associated data that I want to grab out of that thing. So this patty count that's up in that magenta, that's only going to be set to the patty count if the case of this thing is a hamburger. And in this case, it's not. It's a drink right up there. And notice that the things that we do there don't have to match the names. So the drink, you see where I'm switching on the drink, brand, let brand, that yellow brand. Remember, that was just a string in my original enum. I didn't give it a name. I didn't call it brand. But here I'm saying let brand. I want it to be called brand. These words here, even patty count is different than the patties I had in the other. Here you're just picking the variable you want to use there, and it's going to pull that associated data out. Yeah? Yeah, great question. The question is, for drink right there, do I have to have let brand, let ounces for all of the associated? What if it has 5 associated data and I'm really only looking for the third one? Well, the next slide says we can use underbar. Remember, underbar means ignore this, just like it does in a func. Same thing here. Underbar there means I don't care what the brand is there. And that's why I'm printing whatever ounces drink. I'm just printing the word drink. So yeah, the answer is yes. You can put underbar for all the ones you don't want. And these associated can be any types that we want in here. And another thing about enumeration is iteration. I mean, can you imagine sometime I might want to actually have an array with all the various cases in there? Like I've got my Tesla here and I'm reporting the sales numbers. I want to do basically a for loop on all the cases. This is the first time we've ever seen a for loop, by the way. That's what it looks like. We'll talk about for loops later. But this all cases is a static on the type. Tesla model is a type. It's an enum. And dot all cases, it returns an array of all the cases in that order, by the way, X, S, 3, Y, in that order. And to get this all cases thing to exist, though, you have to say you behave like a case iterable. Enums that behave like a case iterable have that little static var. And it's not like behaves like a view where you have to do var body. You don't have to do anything. You just get it. If you say you behave like a case iterable, you get that all cases static. We'll do an enum with associated data on Wednesday, so you can see it in action. All right, generics. Okay, sometimes we just don't care, is what I say right here, and that's true. Because Swift is strongly typed, everything has to have a specific type. However, occasionally we don't really care what type something is. We know it needs a type, but we don't really care what it is. And array is the canonical example. I experiment in this class with showing other examples of things, but this is the one that people really understand, is that an array is a type, it's a struct, and it contains things that it doesn't care what they are. It could be an array of classes, it could be an array of structs, it could be an array of enums. It absolutely does not care. However, it needs to have a name for that type, because how else is it going to declare the function append? Append appends an element. The red question marks there have to have some type there, even though it can be any type in an array. So how does this work? This works through this system we call generics. And the way array declares itself is it says, I'm struct array, and in angle brackets right after it says, and here are my don't cares. I call them don't cares, all right? Here are the types that I don't care about, but I'm going to use. Just puts them in angle brackets there. And then it can use that type, that placeholder type, if you want to call it that, to declare its functions, like append. Look, append, it's element of type element. So this is how generic works. It actually couldn't be a simpler way to do this. An array knows nothing about element. It doesn't know whether it's a struct or what the heck it is. It's just a placeholder for a type. Now, when we use an array, we say var a equals array of int. This is why I like to write it as array angle bracket ints, because you see the angle brackets kind of match the one up there, and that's when element gets to be a concrete type. Before element was just a placeholder, but as soon as I declare an array, then it gets to be a concrete type. And that's why I can say append 5. Append takes an int, because the append up above there is defined to take something of type element, and as soon as I said var a equals array of int, element became int. Notice, though, that array has to let people know that name of element up there. That's part of array's public definition of itself, that it has this thing. And it's totally legal to have multiple of them if you want. A complicated struct might have multiple don't cares. That's really not even that unusual. This whole thing, that element thing, we actually call it a type parameter. You can see why we do that, right? Because these are types, like array, and that element is like a parameter that we're passing when we create it to specialize it, to turn it from a generic to a specialized array, an array that actually has a type. And other languages have this. Okay, how many people have seen generics in another language that they've written code in? Okay, actually that's not very many. I'm surprised. But Java has this, other languages have this. It's not that unusual. It's super important in Swift. I mean, I cannot overemphasize how important. The whole system is built on generics. There are generics absolutely everywhere. We use generics in views. You've already actually kind of seen it. VStack, its return type for its third argument was content. And then later we saw where content behaves like a view. That was a generic. So VStack is generic. It will work with any view that you pass it there. There's a lot going on behind the scenes with generics. I'm going to introduce generics to you a little piece at a time. So this is the basic use, the array kind of use. But when you throw protocols into the mix, you can really make generics be super powerful. All right, optional. I said this might be the most important, or not most important, but it might be the most often used data structure in Swift because it's used in so many different cases. And it's used because Swift demands that every variable has to have a value at all times. Optional is for any time you have a variable who at some point in its lifetime, maybe at the beginning, maybe at the middle, maybe at the end of its lifetime, is in a state that's like undetermined or invalid or I don't know or something like that. That's what optionals are for, and it's just a type. Now, in other languages that don't have a type optional, they might use -1 to mean this is an invalid state, right? Because maybe it's supposed to be an integer that's a positive integer or something. Or they'll use a null pointer. That's a common thing to do, is just have a null pointer mean this is not set right now, but it's eventually going to point something, so it's eventually going to be something. Well, Swift doesn't do any of that. We don't use null pointers. We don't use -1 when we mean invalid number. We use optionals. It's a formalized idea. Optional is a type. It is a type. The optional can only be in two states, set and not set. That's it. That's the only two states it has. And in the set state, it can have some associated value going along with it, right? Because obviously if it's set, it has to be set to something, so there's the something that it's set to. Now, these sorts of values, these optionals are so common that Swift adds a lot of syntactic sugar to it. Remember what syntactic sugar, you know that phrase, is stuff that the compiler will put in there to make your life easier. And I'm going to show you how it works first, and then we'll go talk about the syntactic sugar. Now, you probably have already guessed what an optional is. Anyone want to hazard a guess? What do you think an optional is? What kind of thing is it? No? An enum? Is that what you said? Bonus points. Yes, it's an enum. I gave you two clues. I said it had two discrete states. That's what enums have. And I told you it has some associated value with it. We know that enums have associated data. So yes, an optional is just an enum with a generic associated value. So optional combines what you know with enums and associated values with generics. So it has an associated value that is generic, which is kind of a cool combo of all those things, enums and generics and associated values. So an optional looks like this. Enum, optional, generic over T. It uses T as the name of its generic thing, like array uses element, it uses T. And then it has two cases, case none, just normal case of an enum, and then case some, which has associated value of type T. That is optional in all its glory. That's all there is to it. And so you can see that something that's of type optional can only have two values, .none or .sum with the associated value that goes along with it. And that associated value can be any type because T is a placeholder. It's a generic. It can be anything we want right there. Some examples of optionals. Where do we use optionals? One real common place to have optionals is when we're looking something up. We're looking something up in a dictionary or in an array, and we might find it or we might not. And if we don't, we have to communicate back, couldn't find it. So we just make the function that looks the thing up, instead of returning the thing it's looking for, it returns an optional of that thing it's looking for. Here's a really good one, first index of. First index of is a function, a normal function on array that looks for the thing you pass it and returns the index into the array where that thing is, the first index, because it might be in there multiple times. And of course, it might not be there. Like in this case, colors is an array of colors, blue, red, green, and yellow. And I just said, give me the first index of orange. Well, orange is not in that array, so I have to be able to return it's not. That's why the type of index, the type of the return value of first index of, is optional int. Optional, and then the little angle brackets int. We just turned that generic optional into a specific concrete optional. This is an optional where the associated value is an int. You see why first index of returns an optional int instead of just returning int? It has to be able to say, I couldn't find this thing. Same thing with the array var. Array has a var on it called first. The var first is a computed var, and it returns the first thing in the array. So it returns something of type element, because arrays have elements in them. But it has to return an optional element, because the array might be empty. If the array is empty, then the first element is nothingness. So I have to return, there's nothing in there. we use it all over the place. Dictionaries, for example. We haven't talked about dictionaries. You're probably reading about it in your reading. When you index into a dictionary, it returns an optional, because a dictionary is a key value hash table thing. Might not be any hash for that thing in there. Also, variables that don't have a value until later in their lifetime. Maybe there's some variable that doesn't have value until you click on something in the UI, and then it gets a value. It starts out in the none case, and then when you click on the thing and it gets a value, now it goes to the sum case with the value that you chose. Lots of uses for it. We'll learn by discovery quite a bit about these optionals, and we'll just be using functions all over the place that return optionals. But now let's talk about that syntactic sugar, because this is so common to do this that we don't want to be typing optional int all the time, and we don't want to have to say optional int dot sum parentheses. That's a lot of typing to do something that we're doing all the time. So here's my optional. I've got some code down at the bottom, and we're going to talk about each of the pieces of syntactic sugar. And the first one is declaring a variable to be of type optional something. And we do that with the question mark. So look at these three variables down at the bottom here, var hello. All three of them are of type optional string, optional angle brackets string, an optional enum whose associated value is a string. That's how we declare it. We don't say optional angle bracket string. We would never, no one would ever type that. We would say string question mark. That's optional string. On the right-hand side, you can see what it would look like without the syntactic sugar. We don't do it that way. You can assign values in the following way. There's a special keyword nil. If you set an optional string to nil, it means the none case. And that is exactly the same as saying dot none. It wouldn't even be wrong to say hello string question mark equals dot none. That would work, because that's what's going on. But we use nil because nil has a special place in the hearts of computer programmers. We know nil pointers. This feels like that, so we're using nil. But you could say dot none as well. That would work. And then if you want to put it in the sum state, then you just give it the associated value. If I say hello string question mark equals hello, then I get optional string equals dot sum of hello. So now it's in the sum case with the associated data I gave it. One thing that's really interesting about optionals is the only type in all of Swift that starts out with a value. All other variables of all kinds have to be given a value from the start, but optional always starts out nil. So if you have a struct and you say var hello colon string question mark, you don't have to say equals nil. It is nil. It starts out as nil. Now, how about getting the value out of that optional? Because we got an optional, it might be not none, it might be some with a string in there or something. How do we get it out of there? Well, there's a couple of ways to do it. One is force it out of there, okay? Force it is exclamation point. So hello is an optional string. It's an enum. But if I say hello exclamation point, that means go in there and get the associated value for this thing. And if it's not in the sum case, crash my app. So this is truly forcing it out of there. It's a very violent way to get it out of there. We don't use this very much because we don't want our app to crash. But you know what? Having your app crash, especially when you're in development of your app, not the worst thing in the world. Like if you have something and you're just sure that hello should never be dot none here, ever at this point, I'm going to put exclamation point, and that way during my testing, if it crashes, I'll have the debugger right there looking at it. This thing that should never have been nil. But obviously, we don't do this very much. Raising an exception in the none case is a little bit extreme. So this is the way we mostly get information out of optionals, is we use if let. The idea here is we're going to let some variable equal our optional, but only if it's not none. We combine the if and the let in that sentence I just said to say, if I can let safe hello equal hello, then I'm going to print safe hello. Otherwise, in the else case, I'm going to do something else where I don't need hello because hello is in the none case, so there's no value for it. The switching of that, you can see switch hello. In the case of none, I'm going to do something else down at the bottom there. In the case of some, I'm going to do whatever I wanted to do with that data. One thing I don't put up on here, but it's kind of cool, is you can say if let hello. Open curly brace. Not if let safe hello equals hello, but just if let hello. That's like saying if let hello equal hello. And that creates a new hello that is the sum value, but only inside that curly brace. So that's it. That's how we get the value of it. And there's one other thing I want to show with optionals, which is the nil coalescing operator. And this is a way to say, let some variable equal an optional, or if that optional is nil, use this default value. So you see I have let y equal x, question mark foo. That means y is going to be the sum value of x if it's not nil. Otherwise, it's going to default to foo. All right, now that we know about optionals, let's talk about failable initializers. So it's actually possible to create an init that fails. And the way you do that is you say init question mark. And in an init question mark, you do the normal things you do, initialize the variables, but if you realize at some point, oh no, I can't do it, then you can return nil. And in a failable initializer, the people who are accessing your thing need to be doing if let or something. So, for example, I have a struct vehicle that has a failable initializer. It takes a type string, which is the type of vehicle, like quote car or something like that. And if there's no such thing as a quote car, then it would fail. So then someone creating a vehicle has to say if let car equal vehicle of type car, then do something. If vehicle of type car doesn't fail, it doesn't return nil, then you can do something with the car. Otherwise, not. Okay, extension. Extensions, we're going to talk about really quickly here. Swift allows you to extend, meaning add functions and computed vars, other structs and even protocols, and certainly enums, externally. So you don't have to have the source code to it. So that means you can add extensions to colors and views or any arrays, anything you want. It's super important for protocols, which we're going to learn. All those hundreds of view modifiers were added to the view protocol with an extension, because protocols have no code. Protocols are just which functions we're talking about, no code in them. To actually have functions in a protocol thing, you have to add it via an extension. So extensions are incredibly important. But for our uses, we're not going to really design protocols and add functions. Mostly, we can use them for convenience. For example, in assignment 2, one of the challenge modes is for you to convert colors from a string to a color. And you might want to add an extension to the color struct, which gives the name of a color. And I'm going to talk about that in the next slide. But you can do this. You're allowed to do this. Add a computed var. It has to be computed. You can only add computed vars. You can't add stored vars to things with extension, but that's how you would do it right there. And so sometimes we add extensions to simplify code, just to make our code read a little more clearly. We can add our own view modifiers to the view protocol. That's no reason we can't add some too. Usually we would add one that combines other ones. Sometimes we'll make an array of things of a certain type, like if we had an array of match. Wouldn't it be cool if I could add a var exact count that would just return the number of exacts in there? And we also sometimes use extension to add UI code to our model. Because remember I said the model and the UI are separated. The model is totally UI independent. So if we needed a var or a func in our model that was a UI thing, we can add it via an extension in our UI. The fact that we're adding the code in our UI makes it UI code, even though we're adding it to a struct that's part of our model. And we'll see an example of doing all these things with extension down the road. And I just want to say a little more about this extending color in assignment 2. Again, the challenge mode is to get AI to help you to write this code that I'm kind of stubbing out right here, to add a failable initializer that takes a string and returns a color, but it might return nil if there's no such color, and then also add this var name that returns the name of a color. And I suggest doing it just for the built-in colors, like green and blue and yellow, right? One could imagine doing it for all colors, using RGB values or something like that. It's up to you. So that's it. That's all we got for today. Any questions about that? So in our next lecture is going to be the opposite of this, all coding all the time, okay? No slides, I promise, next time. We're just going to build our CodeBreaker model, make our CodeBreaker work, and then your assignment 2 is going to be to enhance it to be even more powerful CodeBreaker, okay? All right, I'll see you on Wednesday. If you have questions, as always, I am here afterwards.